virtual memory. I don't think I can complete the chapter 9 today, but I try. Okay, but definitely I'm going to complete the main part of the page replacement, which is required to start the last lab, that is implementing the page replacement. So if we have a time, I'd like to explain a little bit about the project description. Okay, so this is the virtual memory. So mainly we talk about what is the virtual memory. It's a separation from the user logical memory from the physical memory. Anyway, the main reason we are talking about the memory management is the lack of the space on the memory. So memory is not enough to accommodate the multi-programming operating system. The number of processes over the, why don't you check the laptop or even cell phone, is easily 100. So is it enough to accommodate all the processor at one time in the memory? Definitely not. So that's the reason we consider the virtual memory space. So the main problem of the memory management based on the page and virtual memory is we need to find the victim page. Easily the number of physical memory is filled. There's no free frame. So in case there's no free frame, how can we displace the page? How? So we need to decide one of them as victim page. Then how do we decide the victim page? So one naive way is, did you take the data structure course, advanced data structure? You should have. This is required that 101, 102, and data structure course. I think you did. So you took the data structure course, right? What is the easiest algorithm that you learned?
I mean, we were using records and blocks to store all information.
And then there are several algorithms that you have learned in the algorithm course or the data structure course. Then one of the easiest one is first something, right? The Q is first in, first out. And the stack is first in, last out, something like that. So whenever we consider operating system algorithm, the first algorithm is what? Yeah, first in, first out. So because anyway we need to consider any algorithm that need to select something. Okay? You need to decide what is a priority. No matter what kind of algorithm you are implementing, you are proposing, you need to decide what is your priority. In case of the CPU scheduling, we consider arrival time as a priority. That is a first in, first out. The oldest one will be selected to move to the running queue from the ready queue. Okay? So first in, first out is not just a simple, it makes sense also. So here when we determine the victim page, so oldest one, our goal is what? For the victim page, what is the best case? The page will not be used for future, right? Then we don't have to bring it again, right? So we'd better select the page will not be used in the future, okay? Then how can we determine? So if this page is the oldest one, that means maybe lower chance to be used again. Maybe, I said maybe, not always, okay? So maybe. So anyway, we determine the victim page. At the time we consider priority as the when was the swap in. When is the time? Swap in, page in, I mean the page in. So that is the page replacement, the first in, first out algorithm. So to evaluate such an algorithm, we are going to use the reference string. So first thing, the first question that I have received regarding to the page replacement is this one. What does that mean? The number. So I simplify the problem. The number means it's a page number. Okay? Page number 1, page number 2, page number 5, page number 5. As well as each number means the contents. So CPU would like to read 2. That means CPU, the page number 2 should exist in the memory, physical memory, something like that. So that is called a reference string. So we are going to use the same reference string to compare which algorithm is better than the other. What does that mean, better, in this page replacement? What's the ideal case? Accuracy? If you can find all pages from the memory, that is the best one, right? Which means no page replacement, which means no page fault. So we are going to consider for evaluation metric, for evaluation criteria, we are going to consider the how many page fault. The more, the worse algorithm. The less page fault, the better algorithm. So that's our criteria. To do that, we need to use the same benchmarking, same data set, same reference string. Okay? So this is we have two sets of reference string. So one is the old one. This one is the new textbook. Use this. So I put the both of them for your understanding. So this is our expectation. The more number of a frame. Frame means what? Page frame. Pages where? Program or physical memory? Physical memory. It's a limited. Then this is the number of 4. Obviously, when we have the small number of page frame, the more page fault, the worse performance. The more page frame we have, the less page fault, the better performance. That's our expectation. Let's see whether the graph is working. So first one is the first in, first out. So what is the victim page in this the algorithm? Oldest one. First in. It doesn't matter how many times the used code reference, it doesn't matter. When the page is loaded into the memory. So how many in this uppercase, how many physical memory page frame? How many page frames in physical? 3. Okay? We have only 3 pages frames are available in the physical memory. Okay? So no more than the 3 pages can be loaded into the memory. So this is our reference string. This is the list of the pages called reference by the CPU. CPU has to access 1, next 2, followed by 3, followed by 4, and so on. Okay? First, this is the common mistake. Okay, many of the students ignore the first 3 parts. Is it page fault or not? Some page fault. If you cannot find the page from the memory, it's a page fault. Because at the first time, it's a nothing. So 1, page fault. 2, page fault. 3, page fault. In case of 4, you cannot find the 4 among 3. So we need to decide the victim page. We need to replace one of them. Which one? How can you select? First in, first out. This one is the first in, so replaced by the 4, page 4, and so on. How many total number of the page fault? 9. Then why don't we increase the number of page frame? Physical memory size will increase. So 1, 2, 3, 4. Then 1. It's good. So no page fault this time. So 1, 2, 3, 4. 2. The reference. That's okay. 5. No. 1. No. 2. No. 3. No. 4. 5. So total how many? 10 page fault. So it's not always true. So this, the expectation, the more page number of page frame, the better performance. Not always. This is called the belays the anomaly. Sometimes it happens. What? When? It depends on the pattern of the reference page. Okay? So here, as you can see here, so once the one is the page out, is called again. Then that one is called again. So it calls more page fault. So that is called the Belady's algorithm. We will see how to reduce such a cases. How to reduce page fault in the case later. Okay. So this is the same algorithm using another the reference string. We have the two set of the reference string, but you can, I believe, easily calculate the number of page fault. Okay. So 3 frame. Then you can actually, if you want, you can draw using eraser, or you can make such a the grid, then check it, and whenever you got the message, who sent the message? I will give the extra point to those who texted him. The more students, the better participation, right? Oh, you did? You know him? Oh, you know him? Okay. Say thank you to him. Okay, so this is slide shows the lady's anomaly. Okay. Why? This is not this way. It's going on. Okay. You should understand later. Okay. Yes.
I don't understand what the base frame is.
What is the what?
The base frame.
Base frame? What is the base?
The number inside the box.
But this one? The 7 means 7. The first time there's no page. It's an empty memory, right? How many free page frame here? 3. We have 3. So CPU would like to read the data 7, which is in the page number 7. Okay? So can you find it? No. So you need to, from your program is like this. So 1, 2, 3, 1. 7 will be loaded here. That indicates the 7. Okay, as I said, the number is to simplify the problem. Okay? As I said, that's the first question that I received from the page replacement. So it's a reference tree. Each number indicates page number as well as the context. Okay? It's in just the slide and our side. In real case, generally this is a real page, and each page has a page ID. Then, okay.
So what is Belady's anomaly? This one?
So for them, I'm going to explain again. So usually, this is our expectation. The more page, the bigger memory you have, the less page fault, right? But sometimes not, like this case.
That's what Belady is saying.
Yes. Why we got the delays anomaly? Because the pattern of the reference string. Okay? Sometimes. So we are going to avoid such a pattern by considering what?
The reference string.
We can group such a reference string together, right? Because in this case, the 1, 2, 3, they referenced together. So why don't we make the group? In case one is good, then why don't we keep the other? It's called locality. We can make the locality. We will see later about such a problem. Okay, next algorithm. What is our goal of page replacement? Less page fault or more page fault? Less page fault. How can we make the page replacement less page fault? We do better replace the page which will not be used longer time in future, right? That makes sense. So because he may not be used in my class, I'm not sure that makes sense. So he doesn't need in my class, right? But in case I need his help, I can call him again. But for future never use, so I can replace his seat by the other student. You see, good example. But anyway, idea is the same. So we'd like to see the future, whether that page will be used or not. So for example, anyway, as I said at the beginning, no way to avoid the page fault. So 1, 2, 3, 4. This time it's a page fault. Okay? Many of the students ignore the such a page fault at the beginning. Then 1 is a reference. Don't worry. 2 reference. Don't worry. 5. There is no 5, so we need to decide one of them. Then take a look at the future. This time, see, 1 will be used later. Just next. 2 will be used the 2 time slot later. 3 will be used 3 time slot later. 4 will be used 4 time slot later. What will be the victim page in this case? So 4. 4 will not be replaced. Okay? This one we'd like to keep this one, this one, this one. Then this is the last one to be called reference. So this is the victim page, so 5. So no, no, no. At this time, we can select the, we don't have future information at the time. You can select any of them, then except the 5. Okay? Yes.
If we swap 1 and 5 instead.
1 and 5, 1 and 5 here. So like this one, reference 3. Then, for example, in this case, 1 is here, we don't have to, right? So this is not page fault still. 1, 2, 3, 4. Then 5 is called. Then 5 not. So we'd like to see the future. 2, 3, 4. 2, 3, 4 will be used. So instead of 1, we can put the 5. That is the optimal solution. Yes.
But I don't understand why you call page fault when you take one value and you put it into
The
the page.
page fault means, so here, so up to this one, in the physical memory, 1, 2, 3, 4. We have 1, 2, 3, 4. So, for example, when CPU, the refer the page 2 is here in the memory. So, CPU can read the data from the memory, no problem. But the next stage, CPU need page number 5. Can you find the page number 5?
Okay, got it.
So it's in the logical memory, your program. Actually, virtual memory, in the virtual memory, you have the 5. So 5 should be page in, okay? Page in, but no space. You need to find the victim using optimal algorithm. Okay, that is the optimal algorithm. Is there any better way? Better than the optimal algorithm? No, this is the best performance. Less the page fault algorithm in the page replacement. Problem?
Can you know
What can be the problem?
How can we determine?
How can?
We determine the future.
Right. So it's based on the future. In real implementation, real operating system, how do you know? You can guess sometimes. Okay? There might be pattern, there might be history. So you can guess, but exactly it's very hard to know the future reference to data. However, using log data, there exists the algorithm to guess based on the experience. Okay? So like sometimes you can use the data mining technique or artificial intelligence technique or machine learning technique to estimate, to predict the future. At that time you need the experience, the history data, right? That makes sense. If a certain program has some pattern of 1, 2, 3, 4, 1, 2, 3, 4, you can guess the future, but not exactly. So also you need overhead, workload to estimate the data. So usually optimal algorithm used for what? Reference. algorithm. Reference algorithm means I have a new idea for page replacement. Okay, this one is better than others. How can you compare? At the time, you can compare with the optimal algorithm. Optimal is the best case. So how much similar as the optimal algorithm? So it's usually used for the reference algorithm. So first one is the first in, first out. Second is the optimal. The next one is, this is another the example of the optimal algorithm using on second reference string. Why don't you try yourself at home? Just like what you have done, okay, every day, right? Okay, the third one is the least recently used LRU algorithm. Very hard to see future. What about the past? Yes, relatively. Not always easy. It's also a little bit expensive, but relatively easier than the future. So it's the opposite. If don't be confused. First in, first out. Consider time alive or time, page in time. However, this one, least recently used one means when referenced. When is the last time referenced? Why don't we take a look at the example, then you can easily understand. The first 1, 2, 3, 4. These 4 are page 4. Then 1. First in, first out, we select the victim as this one. Right? And optimal, we see the future. However, this time, least recently used is when is the last time referenced. So 1 is the referenced code this time. 2 is referenced to this time. So let's say this is a time slot. This is a time slot. 1 time slot. 1, 2 time slot, 3 time slot, 4 time slot. So 3 time slot before, so 2 time slot before, 1 time slot before, this one is just now. Then 1 is again, so no problem. So 4 time slot before, 3, 2, 1, 5, 4, 3, 2. Then when 5 is, this is a time, not the reference string. Still 1, 2, 3, 4. So when we determine the victim page of for the 5, in the first in, first out, we select this one because that is the oldest one. In the optimal, we see the future. Then the 4 is victim. But least recently used one, we check when is the last time referenced. Let's see. 1 is referenced just before. It should be 1. 2 is referenced 2 times before. And 3 is referenced 1, 2, 3 times before. 4 is referenced 1, 2 times before. Which one is the oldest one referenced? That is 3.
Wait, can you repeat that paragraph, please? Can you repeat the whole paragraph?
So let me.
Your thing is least recent.
So here is a 1, 2, 3, 4. 1 is referenced 1 time before, right? And 2 is referenced here, so 0. And 3 is referenced 1, 2, 3 times before. 4 is referenced 2 times before. Okay? So when we select the victim page, we are going to select this one because it's the least recently the reference. Makes sense, right? So priority is a little bit changing. First in, first out, when alive. The lead LRU algorithm, when reference. Then this one will be selected. The victim. Then 1 is here. Then this one is a reset, right? It's a 0. This one will be 2 times. And this one is the 5, so 1. And 4 is 1, 2, 3, 4. Okay. And 1, 2, 5, 4. And 2. So 1, 2, 5, 4. Then this one is a reset. So 0. This one is 1. Okay. This one is 2. This one is 5. Am I correct?
Yes. Yeah.
1, 2, 3, 4, 5. Okay. Then 3 is not, so we can select this one. It's the oldest one, least recently reference. That makes sense. Because if recently the reference one may have higher chance to be called again, right? If we are using the loop, if we are using the something, the reference again, same, the pattern of the instruction may be higher chance, and so on. So 4 is not, 5 is not. So at the time you can check back, look back, see the past experience and determine which one is the least recently used one. That is an algorithm. It provides reasonably high performance, which means less the page fault. Okay, 8 page fault. But if you have the bigger, the longer, the reference string, so usually the better performance than the first in, first out. Problem. Problem. Anyone? The advantage, so it's practically we can implement. Also, it's to provide a reasonably good performance, less the page fault. Problem?
Even though the same page which we are going to use next, we will delete because
It
we have not.
cannot be optimal, but as I said, it's the reasonably the better performance. Okay? What she answered is it's not perfect, it's not better, then it can be better if we can see the future consider, but no way to see the future. There exists one big problem. I already encountered such a problem when I explained.
When after every occurrence we have to check the
Right. So I mistake the one time over here, right? And the second time here. So which means every time you need to check the time. Which one is the least recently used one? It's okay when, even it's not okay when we have the 4-page frame. How many page frame? 1 terabyte size. It's huge. Okay? So you every time you should update. Okay? So that's the delay. That makes the delay of the overall performance. So the problem is how to count this one. Any idea? Yes.
No, I wanted to ask one.
Yes. Any idea? Yes.
I think we can change the, for example, to the first page that being called that time, and it's gonna be if that page is in the, I mean at the tail of the
Tail
frame,
means-
at the
yes.
end of the frame it can be upper or side. There's, and so that the latest recently not used one can be at the end of the.
Practically, we can move the location of
Yeah.
page instead. So his idea is, why don't we move, if that is a reference, move the top. How can you find, where can you find such a data structure? Move top or the move back, low,
Maybe we can use link.
stack. All this one will be bottom. Then if reference, why don't we bring it to the top, right? So top is the least, the recently used one. The bottom is the least recently used one. So instead of the moving around the real page frame, why don't we maintain the one step data structure and keep the number of page frame. If that is reference, then we will move to the top, otherwise down, going down. So that's my idea. Okay? That is used in the real implementation of such a least recently used one. But still, that maintenance is the little bit costly. So one nice way to implement that one is each one has the counter. counter can be implemented as the instruction, hardware instruction. So each one has the data structure, counter, instruction, and keep it. So whenever we have a certain time slot, then the adder, reference, then reset. Okay, that's the one way. But still, it needs a lot of the data structure. So we need the same number of the counter to manage this one. Okay. So another way, is a better way and smart way is what as he suggests. So why don't we use the step? So we have not the series of steps, okay? We have only one step, like this. If reference, the 1, 2, 3, 4, in this case 1 is reference, then bring it to the top and automatically shift down, okay? In the stack area. So when we select the victim is always from the bottom. It's not very difficult to implement a function to call the bottom of the data in the set. Okay, so we can maintain only one the data structure, which is the stack, to manage the which one is the oldest one. Such an idea is used in database also. Database needs the very high hit ratio from the memory. Then, which means most of the time when application access the data in the database, access the memory. Then, how can you determine whether data is in the memory or not? At that time, the least recently used algorithm, LRU algorithm, is used to manage whether data exists in the memory or not. If yes, it's a hit, then access the data from the memory. Oops. Still not easy to get used to the new interface. Okay, so this is another example. It's about same algorithm, LRU algorithm. Okay, so first thing first. Anyway, we need to decide the victim page. For what? To load the page in. In case of free pages, like the beginning of the stage, we can put it. That's also page 4. Then, if you can find the page that you refer, then no problem. You can use it. Otherwise, it will be page 4. Then you need to find the victim. To decide the victim, there are 3 algorithms that we have discussed so far. One is first in, first out. Oldest one will be victim. Second, future. See the future optimal algorithm. If we use the nearly, we'd like to keep it. Otherwise, the victim page. The third one, LRU, optimal, see the future, it's not easy, so why don't we see the past? Then if that one is the least recently used, we'd like to keep, otherwise, the throwaway. That is victim. So that is the LRU algorithm. Okay. So this is the LRU algorithm using the such a stack stack data structure. Okay. So still LRU algorithm need some overhead managing the stack area. So there exists the LRU approximation algorithm. LRU approximation algorithm is based on, still we need to use the counter or the data structure. So why don't we have just a reference bit? Reference bit means each page has just 1 byte of the data. Okay? And each byte has 1, 2, 3, 4, 5, 6, 7, 8 bit, right? So initially it's set as a 0. In certain time, if how many instructions in the microcontroller class or assembly class do you remember so far? How many? Move. Move, definitely you should know. And what else? Increment? Decrement? Jump? And what about the shift? Do you remember the shift? What is a shift instruction? You can? Oh yeah, shift right. I cannot remember it. There are several something, what is the register name? It's a flag, right? Flag, then you can keep, but anyway, shift means, so in case of this one, it's a shift right or shift left, right? So is it expensive or very quickly done?
Very quick.
It's very quickly done. So we'd like to get the benefit of the shift operation. How? So if the page has such a 8-bit reference bit, it can be 2 byte if bit. So it can be 3 byte if we wanna manage the more. So let's say it's the 1 byte reference bit, 8-bit data. Then if this page frame number 0 is a reference, we will change bit 1, the first one. Then shift right, or the other shift, which means the number 2 was like that. 1, 2, 3, 4, 5, 6, 7, 8. Then after reference to this one, shift right, which means 0, 1, 0, 0. This is 1, 0, 0, 0, 1, 0, 0, 1, 0. If you have another one, this 3, it was the 0, 0, 1, 0, 0, 0, 0, 0. Initially actually 0, but I'm pretending that in the middle of the process to shift. Instead of shift, I'd like to add the 0, right? That makes sense. Then, if this one is referenced next time slot, shift, right? And add 1, like this. Then this is 1. And this is 0. This is 1. This is a 0. Like this. How can we determine the bit pace using LRU algorithm in this case? Any idea?
The right mouse bit. The right mouse bit.
Do I need to consider the right move bit? Just find
What is that?
This
highest number. In other words, bit page will be lowest number, lower number. Why? If that one is the reference, it's the most this one is called most significant bit, right? So least significant bit. Most significant bit will be set as 1 if reference. Then shift. So if not referenced, like this one, how many times not referenced? 1, 2, 3, 4. 4 times. So this is the least recently used LRU, the page. Benefit, it looks like the more complicated than the stack or counter, but very fast. Okay? Shift operation, the instruction is fast. So we can use, however, how long can you keep? Only 8 times long, or 16 times long. That is the reason it's called the approximation, LRU approximation. Okay? In case of time, you need to decide one of the tie break value, like for example the lowest number or the first in first out, something like that. That is the least recently used approximation algorithm using reference bit. It doesn't have to be the let's say in bit. Yes.
Every page has that.
Yes.
So what's the benefit of not keeping the counter and keeping it just because of the speed?
Yes. Performance.
So if we have a million page, we'll have a million
Yes.
registers.
But still, it's not a. Yes.
Sounds weird that you only have 8, let's say, counters.
Yes.
Because it's going to be in a huge program with a lot of memory. It's going to be more than 8 times that you need to keep track, like even maybe 100 times, right?
Yes.
Or so what you just keep adding bytes.
Oh yes. So for each, this one, each one actually each byte keep track of the each page.
Yeah.
Okay. But how many times?
8.
8.
And
So
you're gonna-
that is the reason we don't know the older than the 8 times. That is the reason it's called approximation, not exactly LRU. Okay.
And you said that the solution for error is state, right? So if the oldest one at the bottom,
Mm-hmm.
if we see it, we should But in stake, it's always last in first up.
Mhm.
So if you have to take out the bottom one, then you have to empty the whole stake and
Yes.
then.
Mhm.
So.
But
it's-
empirically, I didn't test it, but empirically, this one is so fast and better performance.
No, no, I'm talking about the stake.
Stack?
Yeah.
A stack is you manage to separate the space for the stack. Then you need to move down whenever the reference bit, the victim page is selected. Okay? That is a stack, using the stack. Okay. And there are, even that is not enough, so there is a variation of the LRU approximation algorithm. Okay? There is another one which is called the second chance. Okay? So let's take a look at this. So this is a page frame. Okay? So 8-bit is 2-bit. Okay? So for as he said, what if we have the thousands or millions of pages? So we'd like to keep only 1 bit for each page. Okay? 1 bit. So like the 0 means not reference. 1 means reference. So when you select the victim page, just next victim. Okay, next. Next one. Okay, 1 means it's the opposite. Next victim. Let's see. I think replace any reference bit. Okay, yes, right. So here, okay. So this is the when we select the victim page instead of the managing. Here we have the 8-bit for each page. We are going to manage only 1 bit for each page. Then if reference, we will set as the 1. Otherwise, it will keep the 0. But when we select the victim, we'd like to search as the circular fashion. So for example, so here, in this case, the last one was this one. Then if we select, I think that this one is, I'm going to draw my own. So let's say this is the page and this one is the first time not referenced. If this one is the reference is set 1. Okay? And so right now it's a field. So if we want to find the victim page, we'd like to find the 0. Okay? 0 is not referenced before. 1, it means it's a reference. So to find the 0, we are going to start from the last one. Last reference one. So we will start. Then see this one is not referenced before, so we will select this one as the victim. What if this one is 1, this one is 1, and this one is 1? Then can you find any 0? One time it is 1 circle, you cannot find the victim. Then starting, this one will be victim. So this is called second chance, the LRU approximation algorithm. Second chance means worst case, it will check 1 cycle of the reference bit. Okay? Then select to find. It doesn't consider the exact order of the history, unlike the previous one. However, it's within 1 cycle reasonably, we will select the not used one. Right? If that has been used, it will be set as 1, right? The 0 means it's not used within 1 cycle history. So that will be selected. How long, we don't know, but it will be selected. In worst case, all pages are sequentially referenced. All of them are 1. Then we cannot find the victim at the time. Second chance, second turn, the first one will be automatically selected as the victim page. That is the second chance, the page replacement. Okay? So actually the LRU, using reference bit is not practically used, but the empirically is better than the others, the traditional way. So currently such a approximation, LRU approximation or such a second chance algorithm is used to find the victim page. Yes?
Can you repeat please the second
Yes.
sentence?
So why don't take a look at this example. So when you select the victim, we have a 4-page frame. Okay? 4-page frame, each frame manages the one reference bit. If that is reference used, we will set as 1. Otherwise 0. So 1, 1. So this one is a reference, so 1. The next time, so no free space, we need to find the victim page. How can you find the victim page? We will travel circular fashion from here. So it's a 1, so used, skip. 1, used, skip. Then if you find the 0, this will be the victim. However, problem is all of them are 1.
So you got 2.
Then second turn, the first one will be selected as the victim. Okay, that is the second chance.
If all are used, then you can also pick the very first one, isn't it? What if all the
Mhm.
pages are referenced,
Mhm.
then in the next second chance. you
Yeah,
can
that
always-
first one will be selected.
Yeah.
Yes.
We can pick the first one.
Then we can enhance the such a thing with another bit. Another bit is the dirty bit. Dirty bit. We use the reference bit, dirty bit, or it's called the modify bit. Sometimes the page in the memory, page frame can be modified. Right? Using move instruction, the CPU move the register information to the memory. So it can be modified. So what about in case of modify? What happened? It's not exactly same as the logical memory. So you need to manage it. This data is changed. So we can consider such a whether one. So not only just the reference bit, and also we managing another modify bit. This page is modified. It's a reference and modified. So which means, for example, actually, if the page is modified, this one is set as 30 bit. Until the process who modified this one, there might be 2 copies of the map page. Okay? Then when the current process that modified this page terminated, then this one will be gone. Then you can use this one. Until that time, this one should be served as the for other the process in case of share the page. Okay. So this is the dirty bit and the modified bit. So there might be 2 cases. So 00 means it's a not recently used. It's not referenced. Also even not modified, which means best chance to be victim page. Not modified, not. So if modified means it's accessed, it's used for current process. Okay, we do better keep. So 01 means not used, and but modified. Okay, which means it's currently modified. So we do better keep, but in case needed, it can be victim page. But we do better keep it. Okay, and 10 means it's a reference but not modified. It's a probably, maybe reused. Okay, again. Then 11 means it's a reference also currently modified by the one process, which means if needed, we'd like to keep it. Okay, if your page out, sometimes later you need to bring it because current process is modified. That is the page. There is a process. Okay, so this is an enhanced second, not only reference bit, we can even consider the dirty bit or modified bit to decide the return page.
The modified bit itself is a dirty bit.
Yeah, it's the same thing. It's a dirty bit or modified bit. Also, another method to decide the victim page is we are going to actually counting how many times the reference. Okay, so using the counter. So there are two ways: least frequently used, most frequently used. Higher number, most frequently used, least frequently used. Can we say least frequently used is the victim always? Maybe the higher chance, but not always. It depends on the algorithm. So, but your operating system can use such information frequently based. Okay, using count. Okay, so can skip the some part.